All right, so last week we talked about the bottom end, mostly. I did leave out a component of the bottom end, and nobody called me on it, which was the cam. I did not talk about cams.
Oh.
Yeah.
Why didn't we talk about the cam?
Well, because even though it goes in the bottom end, it's part of the top end. It's part of the valve train, so I haven't talked about that this week. So, all right. No. Yeah. Well, if I did that, that'd be a short week for me. That's all I got. Unless anybody wants to call me on anything, we'll call it a week. Test on Friday.
Everybody good.
I won't. All right. Let's start by talking about pistons. Pistons. What is a piston? Well, hopefully you figured it out now. It's simply a plunger. A plunger that moves up and down in the cylinder barrel. A plunger is a plunger that... I did start the recording, I hope. I did, okay. A plunger, I'll just edit that part out. A plunger that moves up and down. Oh, I did make a video this weekend. Yeah, of me working on the plane. I can show it at break if you want. In the cylinder barrel. It transmits the force of the burning and expanding gases in the cylinder to the connecting rod. So it transmits the force of the burning gases, burning and expanding gases. In the cylinder to the con rod, otherwise known as a connecting rod. So in the next class, 12 and 13, we're going to talk a lot about what this gas is really doing inside of that cylinder, because we're going to talk about carburetors, fuel injection, so we're going to talk about the fuel and the burning. So for now, you just got to know that, right, it's an expanding gas. The fuel and air mixture are going to ignite, they're going to burn, they're going to expand out. It is not an explosion. Explosion is bad and called detonation. All right, about 500 psi. And I found stuff that said the range was somewhere between 300 psi in the barrel to over 1,000. psi. Which now maybe is a good time to talk about this. What does that mean right there? LBS/int pounds per square inch, which is just another way of writing it very lengthy. So you have PSI. There's PSIG, which is pounds per square inch gauge. So it's what it reads on the gauge. What else is there? PSIA, which is? Absolute. Absolute, yeah. So it pulls out the reference to 14.7, right? Okay, because this is 14.7. What's that? Yeah, it starts at 0.
Yeah.
And then, so we're at 14.7 thereabouts. So when our gauge says 0, it's discounting that. And there's PE, PSI. Everybody's familiar with that one.
Yep.
Which stands for?
With the ZERO at the end of it, though. That's my favorite.
That's your, okay. PE, PSI?
Pepsi?
Pepsi?
So I like it with the ZERO.
You got it. I think I probably told that one last year then. So, okay, they are made of aluminum. Our pistons. I don't know if pistons in anything is made of other than aluminum. Made of aluminum. Made of aluminum alloy. According to this note, I don't know, I'll write it just so we have it. Heads of pistons are thicker than automotive pistons because auto is they're water cooled and we have air cooled. So I do know with water cooling, of course, you have a much tighter control on the temperature. It starts right up, you get it, and you hold it, maintain at that temperature. As where we don't, it fluctuates.
I thought aluminum was a really malleable, like, metal.
Well, pure aluminum, 1100, but this is an alloying. I don't know exactly what the alloying agents are, but it's pretty resilient stuff. So, but it's not.
Especially those billet pumps.
Yeah, but you're not heating it up more than what, 400 or 500 degrees. You got to keep it kind of cool. But the other thing about aluminum that's really nice is it has a high transfer of heat ratio, so it transfers the heat very quickly. So it gets rid of it through the rings, into the cylinder wall, into the fins. Oh, well, it's right here. It's 4130. That's the alloy. Made of aluminum alloy. So the heads of the piston, that is, of piston, are thicker than automotive. And that is because autos are water cooled and aircraft are air cooled. Most of them, not all of them, most of them. What is the material? Material is, they're forged out of 4140 aluminum. Or my notes say cast, I don't know, cast of 132. I always thought 4130 was steel, so I don't know about that. I know at Lycoming, they got this really cool machine, and they take a billet, kind of put it in one end, and it runs through and it comes out, and a little ding, and then a piston is right there. They had a lot of problems with that.
What exactly is the difference between forged and cast?
All right. Guess what I just skipped over?
Definitions of forged.
Nobody's going to want to know that. Somebody doesn't want to know that. All right. Forging versus casting. Forging versus casting. All right. Cast, material is heated above its melting temperature and poured into a mold where it solidifies. In forging, you beat the crap out of it. So cast, we'll put that. Material is
Like a mold.
Material is melted and poured into a mold. How's that? Not a cheese mold, but a regular mold. And then forged. Forged. It is physically forced into shape, which sounds nicer than beat the crap out of. Physically forced into shape while remaining solid.
She was forced into that
She was
wedding,
physically forced into place. I didn't.
into her wedding.
In a solid state. There we go. Although frequently heated. Just not as much frequently heated. Forgings normally have less porosity, finer grain structure, higher tensile strength, better fatigue life strength, and greater ductility than casting.
They're better.
So in a word, it's better. Now, this is not to say that it's actually, forced and like it comes out and like, wow, look, that's a nice looking piston, right? It's forced into shape, but then it's cut and it's various other things. Not only that, the pistons that we use nowadays are steel belted pistons. They got a ring of steel in them. So that steel's got to be put in it. I'll talk about that in a minute. Let's see. I should have some pictures. All right, there's piston right there. Now you know. Next. Wow, that just went way, not a piston. That is a piston cooling jet that Lycoming uses. So if you kind of watch how engines are built and what's going on, they often have some means of squirting oil on the back side of the piston. Well, this is Lycoming. They just literally put a oil squirt hole that just sprays across from one side to the other. Well, it's actually right on the back of where the piston is. So, because you can see the bearing right here. So just spraying right into the back of the piston and it cools it. Some engines, they spray out of the back of the connecting rod, kind of across and over to the next one. Some don't have anything like your engine. So we're going to talk about all of these various little parts of the piston so that you understand what each one of it is. I'll probably come back to this slide many times, but we'll talk about the different types of pistons. I feel like that's out of whack. Material. All right. Our pistons are of the trunk type versus the slipper type, which is kind of weird. I'm like, slipper? What the hell's that all about? So we have the, what's that? We have the trunk type. Oops, let me just write what's in my notes, otherwise it becomes just a mess. Trunk versus slipper. Aviation pistons are the trunk type.
Always.
Apparently are the trunk type. I decided to try and figure out even what this trunk and slipper, I had never heard this version before, these words. Trunk pistons transmit the side load to the cylinder wall. So that's what I can come up with. So trunk type pistons, trunk pistons transmit the side load to the cylinder wall. And the slipper, or I found the word crosshead as another word, pistons, have been reduced in size and weight as much as possible. So it appeared that they'd taken quite a bit of, I'll go back here, quite a bit of this area right here and got rid of it. Well, not the piston pin side, but the opposite side. So what do we see? This area right in here, right in there, got rid of a bunch of that. I don't think I got a picture of it. Yeah, a lot of this right here is gone.
Is that reduced for?
You just have to transmit the load some other way. Again, it's automotive. I don't know automotive stuff like that. I work on aircraft. So pistons. Must be lightweight. I think we said this last week about con rods, that they had to be lightweight. What was the reason for that?
To reduce vibration, or
No, it could be heavy and still reduce vibration.
yeah, that's kind of more what I meant.
Constant start and stops is what the verbiage is.
And you kind of have your kind of doubts about that.
I-
The way-
Sometimes people just say stuff and then it just gets perpetuated, and I'm like, I don't know, is it really? And obviously you want it lightweight. It's an aircraft. You want things lightweight, and you don't want. I can see where you wouldn't want a lot of inertia, but let's just take a look at some of the other engines that are out there. If you think about antique engines, which I don't know a lot about, but I used to love going to the county fair, and they called them the one lunger because it only had one piston, and it would, it had a flywheel like that, and it would go for a couple minutes and it would, one power pulse, and it would go for like another, 30, 40 seconds, a minute or two. Geez, when I was a kid in the shop, we had a train piston that was like about that big around. You know, I could barely move the thing. We used it all the time for bending metal around a radius, and it was really cool. But, you know, they had no, you know, still a piston, it's still the start and stop, and that thing weighed 100 pounds, it seemed like, you know? So, I don't know, I just kind of throw that out there before, you know, I perpetuate something. And it must be lightweight because of start and stops. You know, if that was so stinking critical, you know, why did we go to steel belted pistons, which weigh a lot more than non-steel belted pistons? Well, because the trade-offs, you know, made sense. I don't know, and so as I go through books and I write my notes and I do reading and stuff, I just run across this stuff and I'm like, oh, I'll write that because it's what it says. I'm like, I don't know. Then I think about it and I'm like, yeah, I'm not so sure about that one. And I'm not even going to write this right here, but, you know, just what's going through my head right now, it's like, you know, this is all really cool stuff to know. But the fact of the matter is, I don't think any of you in here are going to be engineering pistons anytime soon. And when you do, you can go to engineering school and you'll learn all about it. So what are you here to do? You're here to learn to fix what's there. And it's good to understand this stuff, especially where we're going about the nomenclature and how things fit and stuff like that. But gosh, the one thing I'd want to stress about pistons, you know, it's funny, I'll write it down, but shouldn't have to, use the right one. And you know, when you think that, well, that just sounds so basic. I mean, of course we're going to use the right one. How are you going to use the right one? Well, we're going to go to the parts book, you know, and I'm going to look up in the parts book and say, there's the, you know, this engine and there's the piston. Well, no, not really. Truth of the matter is, engine manufacturers are very delayed in ever updating their parts books. You know, if you were to look up the part number of the piston for my engine in a parts book, it's so old. Be like, that's been superseded like 8 times. But yet it's a new parts book. It's like, well, why do they do that? Well, because they make service bulletins and the M0 manual, and they update that constantly. I mean, it's just at a moment, like, oh, this updates service bulletin, and it has all of the pistons and everything. So number one, you got to have the right piston part number. But number two, it's got to match what came out. All right, because, you know, sometimes you may, especially in Lycoming or the 0320s, somebody put high compression pistons in, or even the difference between the 0320As and Es were low compression, the other ones are high compression, if I remember correctly. So, you know, and each one had a different piston. So you got to get the right piston in there. You got to make sure it balances to the one on the opposite side, so it's the right one that came out. So, like, let's say I'm working on, you know, like an old Continental that had just pure aluminum pistons, no steel belting, and I put a steel belted piston in. I do one cylinder change, put a steel belted piston. That thing weighs way more than anything else. The engine's going to shake like crazy. So, you know, you got to make sure you use the right piston there. And then recently, I saw an accident, or at least it destroyed the engine, where somebody took a piston. I want to say it was because the Continental, like the 520s and the 550s, are pretty much the same, but the stroke is a little bit different. And so the same cylinders, but that piston comes back just a little bit more. And when it comes back a little bit more, so the crankshaft throws a little bit longer. So when that crankshaft throws on the opposite side, it's pulled that connecting rod back a little bit more, and it got a little bit closer to the piston. Well, in those, they actually have to shave some of the back of the piston off so that it clears the crankshaft when the crankshaft comes around. But if you didn't know that, you're like, well, you know, it's like 520, 550, what's the same thing, you know? They put the wrong piston in. And so the crankshaft came around, just beat the snot out of the piston every time it did it. So, you know, it's just little things like that. Make sure you have the right one, you know? They look the same. In fact, you took them and I laid them right here on the table, and I showed you, like, yeah, they're the same height, same everything. And then I rotate them upside down. Like, whoa, one's got a bunch of machining on the bottom. Like, yeah. So, you know, just be careful with that. Must have high heat conductivity. Must. High heat conductivity. Oh, for some reason I thought it'd be nice to talk about this. The three types of heat transfer. Heat transfer. Anybody know what they are? Good. Okay. Conduction, convection, and radiation. Conduction, convection, and radiation. So conduction. Conduction. Transfers heat via direct molecular collision. Well, let's just think if we could do this a different way.
Direct contact.
It is direct contact. I was just trying to think of an example here. So if I had a little hot plate. So, well, let's see here. We got a little flame. Here's my flame. There you go. It can be that color. And I have a little, you know, we'll put a pot on there. We'll fill some water. Look at that, all that colors. This is beautiful right here. All right. So we got the flame going up. Well, where's conduction? Conduction. The flame is going to heat up the pot. Yeah, and then the pot's going to get hot. And that's going to transfer it out here. So I would say that is conduction. It's conducting heat. So now the handle gets hot. So there we go. So back over here. So transfers heat via direct molecular contact. Conducts heat. Transfers heat. What do you want to say? Via direct?
Yeah, molecule.
Direct, okay. Molecular contact action. I wrote collision for some reason. There. Collision is like contact. Contact. All right. Convection. Convection. Who's got a convection oven at home? Well, why is it called a convection oven?
It uses like magnets, like you put your hand on it, it's not hot.
No, that's you have one of those?
Yeah.
Those are cool. A stove. That's a stove.
The oven,
Well, number one,
Induction,
that's a
right?
stove. That's a stove. Number two, it's what? Induction. So close. They make convection ovens.
Convection is like the heating of air, isn't it? Or
It is. It's an oven with a fan in it.
circulating air.
So it blows hot air around. Like I think it has a fan, like in the back wall, and then behind the fan is another heating element, and there's also one down below, of course. But it heats that and blows it, so it blows the hot air around. So convection is heat transfers by such as fluid or air. So heat transfer by fluid or air, which is technically a fluid. All right. And convection, conduction, and radiation.
So when you say like heat transfer by fluid, is that just like any hotter fluid that directly touches it? Or
Yeah.
But
Water,
that would be
air.
Contact.
Huh?
No.
What? I can't understand.
He said it'd be direct
It would be
contact.
direct contact with the fluid if it was. Are you
Not
saying-
necessarily. Well, okay. So like,
Are you saying like steam? Like if something was like steamed really hot?
would it be steam? Steam? Yeah, I think steam would be convection technically, because
Convection is a cross between both. In order to have like steam, right? In order to make that, you gotta have that hot
Yeah.
convection or conduction heat against your pan. in order
Yeah.
to make the
Sous vide's
steam.
a good one.
Yeah.
so let's
Yeah,
see.
that's
So
right,
if we had
that's right.
heat going out this way from the fire,
That would be convection.
that'd be radiation.
Mm-hmm.
Yeah.
Well, it's like the difference between like a toaster oven that's just got an element where you're just putting something in the toaster oven, it's getting hot because it's under that hot element, versus like an air fryer, which is a tabletop convection oven.
Yeah.
It's using the air to aid in the process of heating.
To aid in. So technically speaking, all ovens are the same.
Right.
It's by convection. It's just it heats the air up in the oven, but a convection oven has a fan that blows it around.
Okay.
Which is an air fryer, which then speeds up the process, right?
Okay.
I think. I don't have an air fryer. You guys are rich. I'm
And then
not.
radiators and cars.
You guys some
Oh,
fancy
if
stuff.
you need $4,000
Okay.
is pocket change, you gotta go get an air fryer.
Thermal radiation.
If that's pocket change, can I borrow 20?
Thermal radiation.
$20?
I hate this definition. Thermal radiation generates heat from the emission of electromagnetic waves. I don't know, but it's not the air. It's just the actual heat coming off of something. So, thermal radiation. Generated from emission of electromagnetic waves. Yeah, whatever. So we can take this now and talk. Why did I talk about this? Because the piston has to have high heat conductivity. And just a little bit ago, I talked to you about the conductivity of this piston. How is the piston getting rid of its heat?
Through the oil.
Convection?
Conduction.
Oh, actually, that's something I am going to talk about in just a minute. So let's talk about this. We'll get there in just a second. So what is the temp? The temp inside the cylinder can reach, according to this, 4,000 degrees Fahrenheit. So they say. Aluminum melts at, about that. And I know that for a fact because I accidentally melted a bunch of aluminum. Those crack plates, well, I tried to make them in a kiln. And so, but unfortunately, obviously that heats the whole thing up evenly, and I didn't quite get the concept at the time. And so I tried everything else. I took a kiln, I put it in there, and I had thin pieces. And then I went to pick them up, and there was just melted aluminum. I'm like, well, that melted. So, all right. So obviously, if the cylinder temp can reach 4,000, and the metal can't be that hot, none of it, and aluminum melts at 1220. And so you have aluminum pistons, you have aluminum heads of the cylinder. Honestly, the aluminum is going to start breaking down. I forget the exact number, but it's just around 500 degrees. I want to say it starts to significantly weaken in that neighborhood, maybe a little more. But you got to keep this stuff cool. So how do we get the pistons cooled?
Air cooled.
Heat transfer, obviously. Transferred from piston. All right, let's start. How? From piston to what? To the what?
To the walls.
Right. To where?
The fins,
Which fins?
the cooling fins on the outside,
Well, how to get there?
through conduction.
So we gotta think about that. So from the piston to the rings. Because the piston doesn't really touch the walls very much. Not supposed to. From pistons to rings. Then to the cylinder wall. Then to the cooling fins. Then to the air surrounding it. So what happens if you don't have good air flowing over your engine? It's going to get really hot. And, the nice thing is about cars that are liquid-cooled engines, you've got a temperature gauge which tells you the temperature of the water. And that water is flowing through the whole engine. So if some part of the engine's getting hotter than the rest, what's going to heat up the water? You're going to see it in your water, right? So it maintains kind of a constant thing. It's funny, in aircraft, what we have considering your life is dependent upon that thing not overheating. Like my 6-cylinder has one cylinder head probe. That's just it. Number 3. Whatever. Is it number 3? It was. That's in the middle one. I forget now. I just took it off. But that's it. Just that one. It's like, the other 5. If that one's fine, then apparently the other 5 must be fine, in most of the planes I flew my whole life, I never had a cylinder head temp gauge. The Cessna 140 doesn't have one. Cessna 150 doesn't have one. And you're just flying blind. In fact, the Cessna 150s and even the 140s, the small Continentals, they have these things called blast tubes, and I think I talked about them before, where basically you have the engine baffling, so you have the whole engine, and it's a baffle that goes in the back of the engine, and they'll put a hole like that through the back, so the air comes through the openings on the cowling, would go on top of the engine. The stuff that doesn't go down goes to the back. It hits these holes about yay big, and it has tubes that will blast onto something. So maybe it'll blast onto the alternator or another accessory. Well, Continental, they have it blasting right down on this fitting in the very back of the engine where the oil screen and oil temp probe go. So it keeps the oil temp probe cool. So what's my oil temp doing? It's got a blast tube on it. We'll talk about oil temps here in a little bit, but so you don't know. You're just flying blind. I actually had my Cessna 150. I put a 4-probe CHT EGT, and of course everybody made fun of me. It's the only Cessna in the world with 4-probe EGT CHT. But I wanted to know, and it's kind of like the professor side. It's like I've had to teach this stuff. I want to know what it's doing. Be able to explain back to you what happens when I do this or do that. So I put that in, and of course then I sold the plane right after I put it in. So and it wasn't working very well. So all right. Yeah, actually, I could never get it to work well, and I finally called the company, which, by the way, I bought. It was Electronics International, and huh?
I know. So
they're the nicest people. They really are. And I had the gauge, and it's like I thought it was the wiring, and I thought it was my fault, and I kept troubleshooting it, and then I finally called them up. I'm like, yes, what's going on? And they're like, oh, well, it sounds like you just got a bad processor. Why don't you just send us the gauge? Like, oh, okay. So I sent it to them, and they called back a couple weeks later. Oh, yeah, you had a bad processor. You're out of warranty. Don't worry about it. We just took care of the whole thing. We'll send it back to you. We even pay for the shipping. So I'm like, what else could you ask for? Well, I did, but then I sold the plane, and then so then I actually had to deliver the gauge to the new owner. Here you go. Have fun with it. And it works now, apparently. So all right, so it's got to do that. Yeah, it's just kind of funny how we don't get to know what's going on, which is why I'm now investing the money in my aircraft to put in a 6-probe thing. So, all right. So number one, we got to get it through there. I could go on and do an entire sermon, as my daughter would say, about preach it. I could use some of that every now and then, man. About how so many mechanics, not us, of course, or anybody in this program, completely ignore the baffle seals on the engine. Oh, that's a whole nother, that's next week. So if I don't, so they're very important baffle seals. When I bought my 182, I flew it home in the winter, summer. I flew it home, put it in the hangar, and I said I'm not flying it until it gets new baffle seals. So, yeah. All right. Also from piston to the oil. I showed you have oil piston cooling nozzles, or maybe the hole drilled in the back of the connecting rod cap sprays on it. See, the oil sprays, literally spraying around the back of the piston. So you get that oil, then we'll pick up the heat. Some of these pistons even have a waffle pattern in the back. It looks like waffles. And then the oil looks like syrup, so you want to eat them. So from the oil, and then so it gets collected in the oil, and then the oil, in theory, gets cooled. The smaller Continentals, it's just, I don't know how it gets cooled. It's in little blast tubes, that's how. Bigger engines have oil coolers on them, but not smaller engines. Let's see, to oil, and then possibly to oil cooler, if it has an oil cooler. I said that some pistons have cooling fins under the head. And I said some engines have piston cooling nozzles. You did what in your nozzle? Never gets old. Piston. All right. Yes.
Do you have any examples of like pictures with the cooling fins underneath that?
I could just get a piston and show you. We have plenty of them back there. I don't think I have any pictures. Let's see. You just want to look at my pictures ahead of time. No, it doesn't appear I do. No, well, I just saw it. That's the lecture right there, guys. Ready for the test? No. I can draw a picture though. Yeah. So here's the piston, and then you have the piston pin boss, and you look down here and it looks like this. There you go. I mean, that's just like when you see. Oh yeah, it's just like you're drawing.
Amazing,
All
man.
right.
Amazing drawing.
And that's lifelike too. All right.
Waffle with 2 things of
So
butter.
pistons.
Why would you put the butter?
Why is the butter not the center?
Must have excellent bearing characteristics.
It helps it cool. You wouldn't understand.
Characteristics. Why? Because the pistons are actually rubbing on a lot of things in there. Well, not a lot of things. They rub on the cylinder wall. Cylinder wall, 2 piston. Got that rubbing there. Also, you got the piston pin running in there, so you got the piston pin in the boss. It's not, doesn't have bushings. So you have that steel piston running right inside the piston, steel piston pin running in the piston. And of course you've got the rings sliding around moving forward, so, and the ring 2 piston. So you got all that going on in there. And they hold up remarkably well. I don't think I've ever seen a piston pin boss wear out. Yeah.
Is the bearing characteristics while it's lubricated, or is that if there isn't lubrication, how well it slides over it?
Well, it does need some lubrication in those areas, or you're going to run into trouble.
Yeah.
But what they have done, and this is an interesting note. Let me see. First picture should have it. They don't.
Rings
This is like an old picture. So if you look at a modern piston, this is all going to be black.
Yeah.
That's all black right
Yep.
there. Yep, you agree with me?
Yep.
What is that?
Carbon.
Nope. Brand new piston out of the box.
Oh.
Steel.
Paint.
Treated, it's
Nitride.
Yeah.
What is nitriding?
Gas.
The heating.
Heating. What do you nitride?
It's ammonia.
Ammonia. Yep. And then what's that for?
Hardening.
Hardening. What kind of material?
Steel.
Steel.
Steel?
Yeah. I don't think you can nitride aluminum because you heat it up to what 1,000
Oh, yeah.
degrees. So.
It'll melt.
No, it's moly coating. It's a molybdenum grease, moly grease, but it's a coating, and it doesn't rub off on your hand. So I don't know. I've taken pistons off that have been running a couple hundred hours, and there's still some left. So yeah, they put a moly coating in there now. That's really common. Don't try and take that off.
If that wears off, do you replace it? Like the
No.
coating, or you just replace the whole?
No, because a lot of pistons don't come with that.
Okay.
You know, and for many years they didn't have that such a thing.
Yeah.
So it just you need a little film of oil, but it's still, even if you have a film of oil, it's there. You know, if you think about the piston pin in the piston pin boss, what's that clearance on that? Under 2/1000 of an inch?
Man.
There's not a lot of oil getting. You know, there's some, but not like it's a huge film of oil. All right. Let's talk about the nomenclature. Parts of a piston. And things to know. Ooh, here's a good one. What does campground mean?
It's usually you take your family
Yeah,
on
yeah,
vacation.
that's where you go camping.
That's where you go camping. That's the best I've heard yet. Went to the campground. Had picnic benches and all kinds of stuff. I think that's a campground, but okay. Campground. Anybody know what campground is? I should be. Where's group number one?
Wears down.
Well, group number one finished their inspections. You have campground pistons?
What are you talking about?
Well, I don't think that word is specifically used in your in the manual, so you're excused from it. How did you measure the diameter of your piston? Where did you measure it? Which
9 degrees from the
pin boss?
Yeah, very good. Okay, excellent. Do you know why?
That's the widest part.
Because it said in the manual.
That's the perfect answer. That's exactly what I'm going to say. Because it says so in the manual. Well, let me tell you why it does that.
Manuel.
Because, okay, so you have the piston pin boss, where the piston goes in, the holes, right? That's the piston pin boss. And they want you to measure it 90 degrees of that. Campground pistons are not perfectly round because they have different masses to it. There's more mass in line with where the piston goes through. So as the piston heats up, which side is going to expand more?
The outside.
The side with
90 degrees.
the side with the mass,
Oh, yeah.
right?
Yeah.
Side with the mass. So if you measured it, you're going to see the piston pin boss area is kind of narrower, and 90 degrees to it's a little bit wider. That side doesn't expand so much. So they want you to measure it there when it's cold. And then the other side is not so much. So let me see, cross section perpendicular. Wow. Cross section perpendicular is greater than inline with piston pin. That couldn't be worded much worse, but cross section perpendicular I'm going to change it to piston pin is cross section perpendicular piston pin is greater G-R-E-A-T greater at room temp. There we go. And so if I did this, the piston pin boss, that's where the piston pin goes. But this is bigger. Bigger. Why? Because this has more mass where the piston pin bosses are, and so when it heats up, it will expand more than it is with in line my arrow. So then what operating temperature the piston becomes? Say round. Round, very good.